Okay then, so we've shown now that this exponentiation, where we exponentiate everything to the power of a, basically gives us a functor, because now we've shown this other kind of functor law holds, that the image of the composition is the composition of the images. Okay, so what we want to do next is to look at another way of doing internal composition, and it's a bit more complicated and it's a lot more general. Okay, so I'm just going to sort of introduce this now, and I'm going to come back to it later. So one thing that crops up a lot when we're doing this kind of I mean, the exponential is the adjoint to product. So products come up a lot, and a lot of sort of identities and things involved in the product come up. So we've been dealing a lot with what happens when you do the product of two objects, but there's also such a thing as a product of three objects. And if you have two such ways of doing the product of three objects, they're isomorphic, but it's often useful, in fact, it's the way we generally think, is in terms of binary product. So if you want to do the product of three objects, A, B, and C, you can do the product of B and C and then do the product of out of A. So you get A times open bracket, B times C close bracket. But of course, there's another way you can do it, which is open bracket A times B close bracket times C. And these two ways are both isomorphic, and there's an isomorphism between them. Now, it's nice to be explicit about what this isomorphism is. And so I've drawn it here, written it in red. It's this red arrow, and then the blue one's going back. So if you think about the logic of this, it's quite sort of straightforward. So say we have an arrow into here, sort of a generalized element of this. How can we change it into a generalized element of that? Well, if we take the first part, that'll give us our A, and we want to sort of wrap that in this first bracket here. And then if we look at the second part, so that we do P2, and then we do P1 dash, that gives us the B, and again we want to wrap that in the first bracket over here. And then if we take this and we do P2, that's looking in the second bracket, and then we do P2 dash, that gives us our C, and that wants to go on its own over here. So you can see there's a source of correspondence, and this is just going the other way. Now, we want to sort of formally show that we have an isomorphism here. So composing this big red arrow with this big blue arrow gives the identity, and if we compose them the other way, we get the identity of A times B times C. So let's just show that doing this blue arrow, this big blue arrow after this big red arrow, gives us the identity of A times B times C. And since the situation is symmetric, you could then use similar reasoning to work out that composing them the other way gives the identity over here. So let's show this thing I was just saying. So we want to show that doing this blue arrow after doing this red arrow gives the identity. Now, I'm not going to talk through all this algebra. You can sort of pause the video and see that it makes sense. Basically, we're just using, I think we're only really using two different sort of algebraic ideas. One is that we have this idea that in general f comma g after x is fx comma gx, so we can kind of take the x inside the brackets, and we're doing that quite a lot. So on this first step, we sort of take this red thing inside here and take it inside here. And that's all we've really done on that step. And then we're just sort of evaluating. So for example, when we do Q1 on this, we just get the first part, which lands here, and so on. And we do that sort of picking this thing up and putting it inside the brackets over here, and then just evaluating these projections on the brackets to take the different pieces. It boils down to this. Then over here, we do a bit of a trick. So we do the kind of opposite thing. We take this P2 out of the brackets and put it over here. And then these brackets are P1 dash, comma P2 dash, which is just the identity of B times C. So this just becomes P1, P2, which is just the identity of A times B times C. Okay, so we're basically just using that law I wrote up here and the fact that, for example, P1 dash, comma P2 dash is the identity of B times C, and that kind of thing, that when you just have the two projections and they're the only things in the brackets, then it's basically just the identity. Okay, so that's that. And now we're going to use it to define this sort of more general method of composition. So basically, the operator that we want to define, we want to take an arrow from A to B and an arrow from B to C and compose them to give an arrow from A to C. So we want to make this kind of composition machine that's based on exponentials. Now, I'll just give you the definition. It's defined to be the transpose of this. So this is the isomorphism I was just talking about, which changes the product of these three objects in this form to the product in this form. So we're just sort of using the associativity of the product, if you like, and it's that isomorphism I was just talking about. So we do that, and then we do identity of C to the power of B times the evaluation arrow. So we're evaluating here, and then we just get something that's in C to the power of B times B, and then we just do the evaluation arrow. So it's evaluation after 1 times EAB after this isomorphism, and if we take the transpose of all that, we'll get an arrow that does indeed go from C to the power of B times B to the power of A to C to the power of A, because, you know, when you transpose an arrow like this, you basically just take this thing that you're multiplying by on the right hand side and chuck it up there, and that's the kind of arrow that you get. So it has the right kind of form, but I claim moreover that it basically does composition. So if you have an arrow F from A to B and you have an arrow G from B to C, then what we have is that doing K on this kind of pair, whoops, there should be a lowercase k there. This k I just defined, okay. So if we do that on this pair of G dash comma F dash, so if you sort of pair of points in here, or if you like an arrow from a terminal object to this, then the result is G after F, the name of G after F, okay? So basically this is doing arrow composition, but it's doing it by names. And moreover, this is actually going to be associative, okay? So sort of applying this is an associative operation. So that's all good, but I haven't really proved it. And as I say, I am going to come back to this later. Now I want to talk about something else, which is basically the idea of these, well, one of the ideas of these Cartesian closed categories, because what a Cartesian closed category is a category that has finite limits and also exponential objects. And when you have those two things, you get a lot of nice kind of algebraic relationships. The main one, which I haven't really talked about very much yet, and I won't talk about for a while, is that A times B plus C equals, or is isomorphic to, A times B plus A times C. So we have this sort of distributivity law holding, but I'm not getting into that yet. But I do want to show that some other sort of fairly natural kinds of algebraic relationships hold, which sort of hold for numbers, and yeah, it all looks quite natural. So one of them is that an object to the power of the exponential object, which we write, sorry, an object to the power of the initial object, which we write as 0, is going to be isomorphic to 1. So we do have this kind of thing. Now, yeah, we have that b to the power of 0 is isomorphic to 1. So how do we show this? Well, basically, we use this sort of isomorphism notation here. So we mean that there's a sort of isomorphism between arrows from A to B to the power of 0 and arrows from A times 0 to B. Well, we can see that because of this kind of exponential relationship. So we're using the presence of exponential objects here, really. Well, of course we are, because it's there. And then, we can freely sort of change around the order of a multiplication doing this kind of twist operation, which is an isomorphism from A times 0 to B times 0. So we can change this to be an arrow from A times 0 to B. And then if we again sort of do exponentiation, we get that that's equivalent to an arrow from 0 to B to the power of A. And the point is that 0 is an initial object, so there's only one arrow from 0 to B to the power of A, so sort of exactly one arrow. So consequentially, the consequence of that is that there's just a single arrow from A to B to the power of 0. So there's a single arrow into B to the power of 0 from any object, which means it's isomorphic to a terminal object. Okay. Here's another result which shows that this initial object is acting kind of like a zero, or, you know, in the category of sets, it's an empty set. The category of sets is a Cartesian closed category. And, you know, again, it's acting like yeah, it's acting like a kind of empty set or something, because we have that if we do the product of it with any A, then we get something that's just isomorphic to the initial object. Now, this is interesting, I think, because the proof of this does involve using exponentiation, even though it looks like it's got nothing to do with exponentials. Okay, so we have that somehow the presence of these exponential objects has a kind of knock-on effect and makes stuff true that doesn't seem like it's necessarily directly related to exponential objects. So here's the proof. If we have an arrow from a times 0 to b, well, that's equivalent to an arrow from 0 times a to b, and that's equivalent by the exponentiation thing to an arrow from 0 to b to the power of a. And again, we have that there's only one such arrow. So we have that there's only one arrow from 0 to b to the power of a, and that means that there can only be one arrow from this a times 0 to this general b. So a times 0 has to act like an initial object, so it only has one arrow to any object. Okay. Here's another interesting result. This one's a little bit more involved. So suppose we have an arrow f from a to b, and suppose that b is the initial object. Well, we claim in this case that a is also the initial object, so anything that has an arrow into the initial object is itself an initial object. And this holds in the category of sets, right? Any set that has a function into the empty set is itself empty, okay? Because you can't send something to nothing in a function, right? So how do we prove it? Well, we use this funny kind of arrow called, well, it's actually very natural. It's called the graph, in the kind of function plotting sense, I suppose. The graph of f, and that's just defined to be 1a comma f. So it's going to be an arrow from a to a times b. Okay, and it turns out that this is monic. There's actually a few things you can say about these graphs, and they're very interesting. You can express them as equalizers and all sorts of stuff, but and they really are like the kind of, it's basically a subset of a times b. And, you know, if you think about this in terms of like plotting a function, it's exactly what you'd think of. But it turns out it's monic anyway. It's a monomorphism. And yeah, we could see that by showing that this is an equalizer and going a long route, but we can see it pretty directly actually. So we want to have the property that if we do it after an x and they get the same result as if we do it after a y, then that implies x equals y. And we can see that this works out because we can just take this x inside the brackets to get this, and these two things are only going to be equal if their components are equal. So we have to have the x equals y. Okay, so it's monic, all right? But the other thing about it is it's also what they call split epic, okay? Which basically just means it has a sort of right inverse. No, I'm getting ahead of myself. Actually, what I'm saying is this. We have the this graph here is monic, okay? And we also, and this graph here is an arrow from A to A times 0. Now, we've just shown that A times 0 is isomorphic to the initial object. Indeed, if you think about it, there can only be one initial. It's a unique isomorphism as well, of course, because there's only one arrow out of this initial object here to this one. Okay, so we have this unique arrow, which is doing this isomorphism we've just discussed after this graph arrow. So let's call that arrow M, that composition. Now that's the composition of an isomorphism and a monic, so it's monic. But it's also what they call split epic, meaning that it has a right inverse. So what we're basically saying is that there's an arrow IA that if we do M after IA, we get the identity arrow of this initial object. Okay, and what's IA? Well, IA is just the unique arrow from 0 from the initial object to A. Okay, so like this. And it's easy to see this actually, because if we go along IA and then we go along M, we have an arrow from 0 to 0, and there's only one, and that's the identity arrow. So that means that M is what they call split monic. And it turns out that any arrow that's monic, that means that M is what they call split epic. And it turns out that any arrow that's monic and split epic is an isomorphism. So let's actually go over that, because that's an important general result. So suppose we have an arrow F from A to B. This is all in general now, so I want to substantiate this last claim I made. So in general, if we have an arrow F from A to B and it's monic, and it's also split epic, which means that there exists a G such that FG is the identity of B, then G is iso. It's an isomorphism. How can we see this? Well, just write this, FGF. Well, we know that FG is 1B. So FGF is 1BF is F, is F1A. And then since F is monic, we know that 1A has to be equal to GF. So we have this and we have this. That means F is iso, with G as its inverse. Okay. And so we have this isomorphism here. We've shown now that whenever we have an arrow from A into the initial object, that means that A is the initial object. Yeah, because we've just constructed an isomorphism. All right. Well, I should say it is isomorphic to the initial object. Okay, whenever it has an arrow into the initial object, it is isomorphic to the initial object, which means it is initial actually. But anyway, okay, so we're sort of collecting these results together, which are sort of showing that like the initial object is acting like an empty set. Now, I should say, actually, that just because we have a Cartesian closed category does not mean that we have to have an initial object. Remember, all we get from Cartesian closed category, we get all finite limits, and we get that there's exponential objects. But we can't be guaranteed that there are initial objects in general. But if they are there, then they satisfy these rules. Okay. Okay, I've got to take something back actually. What this meaning of Cartesian closed um, is actually the meaning of something being Cartesian closed, and what we're assuming sort of is that what it means for a category to be Cartesian closed is actually just that we have all finite products, and we have exponential objects for any two objects. So there. So I suppose we're not guaranteed for there to be co-products. I'm not sure if we're guaranteed for there to be limits, because in order to have limits, you also need there to be we also need there to be pullbacks. Excuse me. We also need there to be equalizers for every pair of parallel arrows. So I've been saying before that, I mean, I do believe we're assuming at the moment. Well, anyway, let's just carry on. Okay, so the next thing that we want to do is to make a connection with pullbacks. Okay, so suppose we have a pullback, a sort of general pullback. Let's see down here, and then we do the product of that with something. So we take everything in this pullback. Excuse me. So this is to do with push outs actually. So we've done quite a lot to do with pullbacks, but there's this dual idea of a push out, which is the kind of co-limit of this sort of part of the diagram here. Okay. And then suppose we have a push out like this. So, I mean, push outs are really the dual idea of pullbacks. And I mean, it's quite easy to show that if you have a pullback and you just multiply all the objects and arrows by A, like this, well, kind of like this, then the result is again a pullback. But then again, pullbacks are both sort of living on the same side of the fence. They're both limits. I mean, pullbacks and products are both limits. They both kind of live on the same side of the fence. But push outs are co-limits. Okay, so what about if we have a push out which is a co-limit and we do a product on it, which is a kind of limit style thing, well, then things are actually a lot more complicated, but we can still show that if we do the product of a push out by A like this, then the result is a push out, and this resulting square. So if this square on the left is a push out, then this square on the right is a push out. So it's interesting how we show this, but to do so, we're going to have to think more about exponentiation. So in particular, this result's going to come in very useful for us. So this is a general idea that if we have an arrow f from C to B, and we have an arrow h from B times A to T, well then we're going to have this result holding, that if we do the transpose of h after f times 1, we get h transpose after f. Okay, so this is really the kind of situation that we have. So in general, when we have arrows set up like this, we have that this kind of triangle here commutes. So how can we see this? Well, it's always a good idea to start these kind of constructions by just drawing all the arrows that we have in a diagram, and we can see what's going on. So we're asked to show that these two things are equal. Well, this top one here is a sort of transpose or exponential adjoint of h after f times 1a. So the word exponential adjoint is synonymous with this word transpose that I'm also using. Okay, so we can sort of think of the transpose of an arrow or the exponential adjoint of an arrow. We mean the same thing. Anyway, so then let's try treating this H transpose F arrow here as if it's a sort of something which is something which we're sort of using for converting from an object to one of these exponential objects. Okay, so let's call this H transpose F, let's call it M. So let's consider what happens when we do evaluation after M times 1A. Well, we can write M times 1A as H bar times 1A after F times 1A. And now we see the connection with this diagram, okay? Because we have H transpose times 1A as this red arrow down here. And we see that if we're composing these two, this black arrow going across and then this red one, and then we do the evaluation, Well, I mean, that's what we mean really by E after M times 1A. And we can sort of break it up into two parts then, because we can think of this last part so we can write E. So, okay, let me start again. We can write we can write E after M times 1A as E after H transpose times 1A after F times 1A. And then we can take this piece here, E after H times 1A, and we see that that's just equal to H using this kind of definition of the exponential objects. So we have that all of this stuff is just equal to H after F times 1A. And so we can again use the definition of the exponential to say, well, the whole thing then must be equal to E after the transpose of H after F times 1A all times 1A. Okay? And then, because there's just a unique kind of arrow which does this, this unique kind of transpose, we must have that this transpose of H after F times 1A is equal to M. And that's what proves our result. Okay? So that proves this, and then it turns out that this is going to be very useful to us for proving that thing about push-outs that I was just talking about. But we're also going to look at another form of this. So let's just suppose now that the transpose of this K from B to TA is H. And then we just use this formula again. So we already have this formula. And then when we do this kind of substitution, we get this formula. And then when we transpose both sides, we get this formula here that K transpose after F times 1A is KF transposed. So we see this illustrated here. When we have an arrow F from C to B, and we have an arrow K from B to T to the power of A, then we have this commuting triangle in blue. So we have that K transpose after F times 1A is KF transpose. So we're going to use this formula, which I call blue hash, and this formula that I call red star, quite a bit in this next proof, okay? So here's the thing then. Now we have those kind of results established. We're going to use them. So this is what we want to actually show, that if this left square is a push outs, then this right square is a push out. Okay, so this right square is just sort of taking this left square and doing the product of it by A. Okay, so we'll do our usual kind of thing we do for pullbacks or push outs. We'll assume we have a candidate. I mean, it's clear that this square commutes, I suppose. You just use the sort of basic rules of composing these producted arrows, and you can show that it's a commuting square because this is commuting square. But we need to show that it has this kind of candidate emulation sort of property. So we suppose we've got this sort of push out candidate T, and then there's this arrow H from B times A to T, and this arrow K from D times A to T, and they make this outer perimeter of this diagram commute. Okay, so we have H after F times A is K after G times, sorry, we have H after F times 1A is K after G times 1A. So then we use this star kind of formula here, because I mean, we really have well, we have that these two things are equal. If we do the transpose of them, we get that these two things are equal. And then we can use this kind of idea here, so we can re-express these kind of forms as H transpose after F, like this. And we can do a similar thing for the K's, okay? So we get H transpose after F is K transpose after G. Now, here's the clever bit. We then, if we look at this left pullback, we have an F and a G, and we've just got these transposes, so we've actually got a push-out candidate over here for this thing that we know really is a push-out square. So we have that H transpose after F equals K transpose after G. And then since we know that this is a push-out square, we know that there exists this unique U such that U after I1 is H transpose and U after I2 is K transpose. And now we use this kind of hash, blue hash result. So if you think about this result that we've shown already, well, just use it, but with, instead of K here, we use U, and instead of F here, we use I1. Well, anyway, sorry, I'm getting ahead of myself. We have that there exists a unique U such that UI1 is H transpose and UI2 is K transpose. Now, if we just take the transposes of these equations, we get UI1 transpose is H and UI2 transpose is K. Now we use this rule. Okay, so now if we just look at this rule blue hash that we've already shown, and we just use it with, instead of K's we use U's, instead of F's we use UI, we basically have this kind of form, maybe for different objects, but the form of the arrows is the same. So we just use this law, and we have the transpose of UI1, which we know is H. By this law, we know that transpose of UI1 is U transpose after I1 times 1. And we have similarly that K is transpose of UI2 is transpose of U after I2 times 1. Okay? So now if we look again at our rights, well, what we want to show is a push-out square. We've then obtained this U transpose here, which acts as an intermediary arrow, because we've now just shown by these formulas, in particular by this equals K and by this equals H, we've shown that these two triangles commute, which is what we need to show. The only other thing we need to show that this is a push out is that this arrow here, this U transpose, is the unique arrow which makes this work. Okay, so let's just do this by assuming that there's another arrow that makes this work, and we can call that W transpose. So if W transpose is also such that it makes these triangles commute, well, then we can just go backwards to show that it's actually forced to be U. So if we assume then that H equals W transpose I1 times 1A, well, then by this blue hash again, we get that H is W after I1 all transposed, and again by blue hash we get that K equals WI2 all transposed. And so transposing these green equations here, we have that H transpose is WI and H transpose is WI1 and K transpose is WI2. But then we're back in the territory of the sort of left push out, the thing we really know is a push out. And we already know that there's just a unique arrow, which is U, which is such that H transpose is equal to U after I1 and K transpose is equal to U after I2. And so it follows that U is equal to W. So that's actually forced. And so indeed this arrow is unique. This sort of arrow here, U transpose, is the unique one that makes this makes the outer perimeter of this diagram, well, makes these triangles commute, makes the whole diagram commute, in fact. So that means that this is a push out, this black square, and we're done. Oh, I just want to say another thing. About this result. So this result basically says if there's an object with an arrow into the initial object in a Cartesian closed category, then that object is itself an initial object. So it follows from this, in fact, that if there's an arrow from the terminal object to the initial object, well, then if you think about it, it follows from that that the terminal object is an initial object. Something that's terminal and initial is called a zero object. And then it also follows that every object will have an arrow into the initial object. So every arrow will be the initial object. And every arrow will also be a terminal object. In fact, every object will be a zero object in the whole category in that case. Because once there's an arrow from the terminal object to the initial object, that means composing it. You know, if you have any other object, it'll have an arrow into the terminal object. And then if there's this joining arrow, it sort of makes everything go degenerate. So that'll make everything into zero objects. So, you know, usually that doesn't happen because most Cartesian closed categories of interest aren't degenerate like that. They have lots of interesting structure, at least in most cases that people like to study.